My name is Paul ter Horst. I'm the area manager Northern Europe. We send out or we organize this in first of out of Northern Europe, but we saw that a lot of people also outside of Northern Europe will attend. So everybody, welcome. Um, I will be introducing Tensar in the presentation in the first time, and then afterwards, my colleague Leo Kuljanski will take over. He's the design manager and he will do the presentation. So, firstly, I want to introduce Tensar to the people who doesn't know Tensar before or didn't know Tensar. If we go look at Tensar, we have more than 700 employees, and although I know that some of the people from the Western Hemisphere, what we call the Americas, will probably also attend. My presentation is only for the Eastern Hemisphere. In that case, we have a lot of offices. We produce all over the world, and the main thing is we start producing it already in 1978. That means that we are a long time already on the market, and therefore I think we're the industrial leader, especially on stabilization and reinforcement. The topic of today, T-value, is a good example of showing what Tensar can do all over the world by introducing also design methods and possibilities to design itself. Next slide, please. To have an insight in the offices, all the gray area, the dark gray areas is where we have physically an office. In almost all these offices, we also have a design department. To give you a little bit inside of Tensar, we not only produce, we sell, but we also design, and we have a big design capability. If we go to looking to Tensar as a product, most of our products are geogrids. That means that we started in the 80s with a Ryalenko grid, and nowadays we have the Interex. We introduce these new type of grids, so I would call the Interex the fourth generation. Most people are still in the second generation, so biaxial grids, we have the fourth generation. Why do we evolve our grids? Mainly although we reduce tensile strength, we increase partial confinement and therefore improve performance. One of the statements of one of our product managers is, it's not what the product is, it's what the product does. So that means that looking at the product data will not give you an insight in what the actual result will be or the performance. Looking to Tensar itself, we will be talking about the Interex, and one of the big things we will do is reduce thickness, but we will reduce thickness, therefore save time, cost, and carbon. But the main thing is, if we reduce or we give a solution that we maintain and improve the long-term performance, we maintain the safety and the durability. Although we are talking about crane platforms at the moment, if we're talking about Tensar solutions, you will see that we do more. The working platforms is there on the top right, but we also do, for example, reinforced soil structures and full road designs. Hopefully, everybody is in now, and Leo Kuljanski will take over. Leo, I will let you introduce yourself. Thank you all.
All right. Thank you very much, Paul, for the nice introductions. Again, also from me, welcome everybody in this webinar from Tensar about the introduction to the T-value method for working platform design. So a number of things that Paul showed you in his introduction will hopefully become a little bit more concrete and insightful during the rest of my presentation. But I want to ask you, before I dive in, is to ask any questions that you might have during the presentation, put them in the chat, and then at the end of my presentation, we'll have some time left to answer those questions that might occur. It is also possible that some of your questions might get answered during the presentation. In that case, you can we'll just skip over them if that's the case. If there, for whatever reason, there is no time to answer questions at the end, or not all questions at the end, we will make sure that you get an answer afterward over email. Right, so let me put up my screens here, and then we can dive in. Put the pointer on screen. Hopefully that will help a little bit. So I'm going to be telling about a little bit of the background on why and how we started developing a new design methodology for working platforms. And then I will spend some time talking about the fundamentals of the applied mechanical stabilization. Then the working platform design itself. This is going to be a very technical part. And we're going to show you some full-scale testing and validation of the design methodology. And at the end, I'm going to be showing you Tensar Plus worked example. Tensar Plus is the design platform of Tensar International, which is available to all of you and more. And of course, as I said, there's going to be questions and answers at the end. Right, we have less than an hour, so I'll try to be efficient in what I'm going to be telling you. So working platforms and piling mats. We first need to establish what we mean with that. So temporary working platforms are an important aspect of many construction projects. They provide a stable and safe working area. Piling mats are working platforms designed specifically to carry the heavy static and dynamic loads from piling rigs, their support cranes and associated equipment. Often placed over weaker subgrades, temporary working platforms are typically built using well-graded, compacted granular fills, such as natural gravels and crushed rock, as well as recycled demolition material. Tensar geogrids can be used in the granular material to stabilize it and thus increase the bearing capacity. So the BR470 has been successfully implemented since its publication in 2004 as a guide to good practice to designers and operators of working platforms. Now, some of you might be already familiar with the BR417 and others might not. But it is a key document for the working platform designs in the United Kingdom, which is written by the Building Research Establishment under the direction of the Federation Piling Specialists back in 2004. The BR470 is not a design code, but it is a good practice guideline to the design, installation, operation, maintenance, and repair of ground support working platforms. The document includes design examples and calculations, provided with numerical examples for different subgrades. It provides general advice on important aspects of site investigation, reconstruction assessment, and site preparations as well. However, there is an acknowledgement from the authors that the application of geosynthetics has not been fully addressed. The BRE also published a supplementary document in 2011 titled The Use of Structural Geosynthetics Reinforcement, a BRE review 7 years on. This two-page review recognizes the benefits of alternate design methods, including mechanically stabilized platforms with geogrids, as long as you design it based on credible and representative research and backed up with well-documented project case studies. Many Tensar proposals are used as an alternative to the illustrative methodology in BR470. We will look if our T-value working platform design method satisfies these criteria. We need to demonstrate that T-value method satisfies the requirements if we are to follow the BR470 advice. So the main question that we're going to be trying to answer today is, does the T-value method satisfy all these requirements? So how do we do that? Well, we need to develop a new method, or we have developed a new method, and I will take you through how the process as we developed it. And for that, we need research, testing, and validation. So what is an applied mechanical stabilization? So this is something you will be hearing a lot coming out of my mouth today. A mechanically stabilized layer, the word stabilization, the mechanically. We also abbreviate that at Tensar to MSL. The main question is, how strong is that? But what is it? So our MSL is a combination of tensor geogrids, as you can see on the picture here, where it is interacting with a stone or a granular, unbound granular material, crushed rock layers on top of it. So to be able to understand what stabilization is, we have done extensive research as Tensar. And what you're seeing here is a 3D printed simulation of a rock that can be monitored live during its testing. So what we are interested in is knowing how stones and granular material behaves while interacting with the Tensar geogrid. And for this, we have cooperated with the Penn State University, where they devised a test setup simulating a piece of a rail bed and simulating passes of a train over some sleepers. In the stones, Tensar geogrid is implemented, and the 3D printed rock full of sensors is placed inside the opening of the geogrid, but also above the geogrid. I can show you some results of these testings that have been done in 2016 based on our third generation geogrids. So what we can see here is the test results or the monitoring results of a stone without the influence of a Tensar geogrid, where we can see on the horizontal axis the amount of simulated passes from a train or a train axle, and on the vertical axis the angular acceleration of the stone. And as we can see, the more passes we have, the stronger the easier it is for the stone to move and to rotate, which in turn causes a loosening up of the granular material, abrasion, and loss of stiffness. If you then compare the test results with stones that are confined and stabilized by the Tensar geogrids, we can see that the stones have significantly less room to move and to rotate, thus limiting deformations, degradation of material, and maintaining a high stiffness, resistance, and bearing capacity. This is what we call stabilization. It is not the same stabilization as chemical stabilization, where we bind stones together, comparable to cement, but mechanically confine particles, unbound granular particles, in the apertures of our geogrids, and in turn these confined stones interlock with the above-lying stones, making a very stiff layer resistant to deformation. So if we take a step sideways to the question of how geogrids usually are, or conventionally are, modeled in sophisticated models like finite element modeling, Fluxys for some of you, then the designers are trying to determine the soil properties of their fill materials and the properties of the geogrid itself. So usually this is expressed as a stiffness value, EA. And while modeling the influence of a geogrid in a structure or a working platform using finite element modeling, we can model the layers as a separate entity and put in a geogrid as a separate entity. Downside of this approach is that those two materials are not interacting in a significant way, because the individual parameters are only used, but not what the interaction of those two construction materials mean. What we as Tensar are interested in is knowing and understanding what the influence is of our geogrids to the fill material that we are using. So, as I said, the classical approach is to have soil properties and geogrid properties, and then have a soil with a tensile reinforcement. But at Tensar, we approach things differently. We want to know is how the soil fill material, the granular material, behaves under the influence of mechanical stabilization. And for this reason, we are still performing, and we have performed dozens of large aperture triaxial trials, where we have a half a meter diameter triaxial cell filled with different kinds of granular material, crushed rock, recycled rubble, gravels, and even sands, including a tensor geogrid, the different kinds of tensor geogrids. And we test them. So this way we can find fundamental properties and behavior of this composite of fill material and tensor geogrid. And what we then derive is the confined influence or the stiffness influence of the now composite material existing out of the geogrid plus granular material. And this influence, of course, decreases, or the properties decrease the further away we are from the geogrid, because, of course, the confinement and the interlock of the individual particles decreases. Using all this knowledge and insights, we were able to devise a constituent model, which we can then use in finite element modeling in Pluxys to make a lot of simulated working platforms. And the properties that we use in the modeling are an increased confinement. So what we can see here in the black curve, this will be the behavior of granular material without any tensor geogrids, where we can see the angle representing the friction angle of the material, and the intersection point with the vertical line will be different than the cohesion. And the lower the bulk stress is, the lower the cohesion. And we can see that this is a nonlinear connection between those two. When we apply a tensor geogrid in granular material, using the extensive large aperture triaxial cell testing, we have derived a much higher confinement of the granular material, which eventually results in the same friction angle of the fill material, but a higher mechanical confinement or cohesion. Depending on the stress level and the vertical forces on the granular material, we have a different properties. We can have a higher friction angle, but a lower cohesion depending on the stress levels. Now, using all of these insights, which have been made available in public papers, available to anybody to review, but also various videos, we have been able to devise the t-value design methodology for working platforms. So now that we have looked at the fundamental research, we can now go to the design methodology itself. So we can take a step back and ask ourselves, why do we design working platforms? Well, I think the answer might be obvious to our average engineer. That is to make sure that we have a safe and economical area to work with, because eventually we want to prevent scenarios as this one from a crane tipping over. Now this video illustrates how easy it can be for a crane or a piling rig to lose equilibrium and tilt over. So the main reason for us as engineers is to ensure that we have a aggregate working platform that is not too thick and not too thin, because too thin will be too dangerous and too thick will be uneconomical. So what are the aspects that we can identify in an average working platform? So we have the pressure of a outrigger or a crawler. We can have the width of the crawler. We have the thickness of the granular layer. And we have some kind of distribution angle through the granular layer. And this is going to be the focus of our new design methodology, to determine the distribution of the loads towards the weaker subsoil, in this case represented as a clay. Next to that, we have the subsoil bearing capacity model. As Tensar, we have not made a new model for the bearing capacity. We are simply using the existing Meyerhof and Prandtl bearing capacity failure mechanisms. But we are focusing on the how much load can we transfer through this mechanically stabilized or even unstabilized granular raft. So the first step that we did was to assess a new relationship between the bearing capacity of the subsoil, the acting forces on the granular raft, and the geometrical ratios, so the thickness of the platform and the width of the acting force. And looking at some existing research from Okamura that has been made in 1998 with 60 centrifugal tests on circular and non-circular strip footings, we were able to derive a linear relationship between the ratio of the height or the thickness of the cross-truck layer and the width of the acting force, so a crawler of a crane, and the ratio of the the ratio of the acting pressure and the bearing capacity of the subsoil. And we can have a similar linear relationship for circular footing. Now, this allows us to make a very simple, elegant formula to describe equilibrium in a system, defined by this so-called T value. So the T value is the angle of the ratio. And on the left side, we can see the relationship for the strip footing, and on the right side of our circular or square footing. And the T value method names comes, of course, from the transfer efficiency through the granular layer. Now, for some, these formulas might look a little bit intimidating. Hopefully for most of us not. What we can see here is simply the ratio of the acting pressure divided by the bearing capacity is equals to the ratio, of course, the T value, multiplied by the ratio of the thickness of the layer and the width of the acting force. When we look at strip footing, the relationship is the top formula, and when we look at circular footings, then we have to square everything. And finally, we need to make a final check for equilibrium to make sure that the granular layer itself will not fail before the subsoil fails. So there's an extra inequality that we need to check for, which is the bearing capacity of the granular layer itself. Now that we have derived this very simple analytical relationship for the bearing capacity, we can go and do a lot of parametric studies using finite element modeling to derive the T-value relationship for different materials, different combinations of acting pressures and undrained shear strengths of the subsoil, and get the relationship for the T-value. And as we can see, it fits very nicely with the existing research. This is the centrifugal research from the University of Oxford and Newcastle. And for circular footing, we have even more data. So in this way, we were able to pretty confidently derive a new methodology for defining the bearing capacity of a working platform without even taking into account a geogrid. So this is simply without any geogrid, we were able to devise the new methodology. And of course, also this one is publicly available for review in a paper. Now, the t-value method, as I mentioned earlier, what is it exactly, or what is this t? Well, the t represents, in simplified way, the transfer efficiency of the loads through a granular layer. And the mechanism that we see is that the transfer efficiency decreases when the subsoil is strong. Now, why is that? So the analogy that we're using is this little gentleman, this very strong man, lifting a relatively light load up and trying to hold it up. So when there's very little effort needed to carry a light load, or one has a strong subgrade, the transfer efficiency is very efficient. The transfer efficiency is very efficient, and we can have a very optimal transfer of loads through the stones, because the stones don't have to work that hard. On the other side, if the load is very high or the subsoil very weak, our transfer efficiency decreases, because the stones have to work very, very hard to get all the stresses transferred through the stones, and the transfer efficiency decreases. In an analog with this gentleman that has to strain all his muscles and is less efficient in holding the heavy load. So up till now, you have seen the example for subsoil that is undrained, but the same methodology applies for a drained subsoil, where we can apply the same approach. The only difference is that instead of having an undrained shear strength, we have now a friction angle and a weight, and the formula for the transfer efficiency, or the t-value, looks slightly different, because the relationships are different and the bearing capacity formula is different. What we can see here is, but you can see a similar effect, that the transfer efficiency decreases with the strength of the subsoil. And again, all of this is available in peer-reviewed published papers. So now we want to look at the influence of a tensor geogrid. So what is the benefit of having a tensor geogrid in this methodology? Well, as we can see here in the graph, without any geogrids, the transfer efficiency follows the following curve. But if we introduce a tensor geogrid, we can see that our transfer efficiency is much higher, significantly higher, for our third generation geogrids. In the meantime, we are producing our fourth generation geogrids, as my colleague Paul ter Horst has shown, where we increased performance. We can see here some testing data supporting this. So our newest geogrids are the best performing geogrids in increasing the bearing capacity of working platforms. And also this is available in the public domain, the research supporting these claims. So now that we have derived a new design methodology for bearing capacity of working platforms, we need to ensure that the theoretical framework is also validated with practical and real scale tests, and thus validated. So I'm going to be showing you 3 validation trials, if I remember correctly. One of the important things that we had to consider when devising these validation tests is the influence zone of the contact area of the testing equipment. In practice, a track can be 1 meter or even 2 meters wide. That means that the influence zone of this force is much deeper than the platform itself. It is important to note that a plate load test with a limited diameter, let's say 30 centimeters, is not sufficient to validate the bearing capacity of the whole system. It will only be able to decide in the stiffness and the strength of the granular layer itself. This is why full-scale testing with a large contact pressure is extremely important to validate any working platform. I want to take you along to Canada, University of Saskatchewan, where we performed a number of validation trials to validate our new design methodology for working platforms, where we dug a trench and had a number of trials with the goal of loading the platform until failure. And the goal of these trials was to validate our unstabilized design methodology, so without any geogrids. You can see here is a relatively small plate, about 1 meter, that is being pressed into the soil. As you can see, a very large counterweight is needed to ensure that the bridge is not lifted, but instead the platform is deformed. What comes now is a little short video of our second validation trial in Krakow in Poland, performed in 2021 on a granular subsoil, so a sandy subsoil. And the video shows how the test setup has been constructed, and what system has been used to ensure that we are able to significantly deform this working platform. The video will take about 1.5 minutes. So in this validation trial, we took particular care to simulate real life circumstances. So what you saw there was the rolling out of the geogrid, the placing of the crushed rock material. And what we're looking at now is some soundings, soil investigation soundings that are being taken through the constructed granular raft. So we have actual behavior after compaction. Of course, also here we did some plate load tests to ensure that the modulus was known. And what we are seeing now is the drilling of 4 holes through the raft to be able to anchor the testing frame into the soil itself. The granular raft or the working platform is so strong that extreme loads are needed to even bring it to failure. And to be able to press so hard down on the working platform, this frame is going to be constructed to counterbalance a hydraulic check pushing downward. Hopefully it is clear to you that Tensar goes to extreme lengths and investments to ensure that the design methodologies and influence of our geogrids is thoroughly tested and validated before we bring it to the market. So what we can see here is a lot of counterweight, and even the crane had to help to push down to make sure that the hydraulic check is pushed downward instead of upward in order to be able to bring this platform to failure. So the final validation trial that I want to show you, this one is much shorter than the video, is a real scale temporary working platform test at the National Buried Infrastructure Facility in the United Kingdom. I can see here the delegation that came to watch the live testing. And what we did here was to simulate less favorable circumstances for the testing of a working platform. You can see here a little bit how the fill material looks like. So this is comprised out of a recycled rubble with about 5% oversized stones, something that is typical to the UK situation. But I can also imagine in a lot of markets around the world where we don't always have the ideal crushed rock mixture at our disposal. The plate that is pushing down this sand subsoil is 1 meter wide and 2 meters long, simulating a realistic outrigger or eccentrically loaded crawler crane. You can see here a sieve curve of the sand subsoil that was used in the test setup and a visualization of the recycled rubble that was used. So, which brings me even closer to the end of this section, which is how do we introduce stabilization to and the t-value design methodology. So for each and every aggregate type, we need to go through the same process because we need to be able to reliably design. So first we start with large monolithic triaxial testing to determine the exact behavior of the fill material in combination with our stabilizing geogrids. We derive a Tensar stabilized soil model, which we can use in finite element parametric studies to derive the transfer efficiency curves and implement in our analytical methodology. And finally, everything needs to be full-scale tested and validated that the methodology is reliable. Which brings me back to one of the slides we started with and the questions. If we can objectively and can we satisfy the objective of a safe design? That our rigorous research and development will contribute to a safe design. It is based on credible and peer-reviewed research that is available in the public domain, and all our methodologies are validated by well-documented case studies. So I'm coming closer to the end of my presentation and nearing the question and answer section. But before I go there, I want to introduce to you Tensar Plus, our design software that is free of charge for anybody. The only thing you have to do is go to tensarplus.com and make a user account, and you can start designing with GeoGrids free of charge. There's a number of modules available to design with, but of course today we are focusing on the working platform. Here's an example of a project from the United Kingdom with a lot of details here on the slides. We have a total area of 5,000 square meters. We have 2 load cases, which are required to be defined according to the BRE 470. And I can show you the final results of the design. And in a moment, I will also show you how that looks like in our design software. So here we can see if we are not to use any geogrids, the working platform or the piling rig in this case would have had to be 1.20 meter thick. But by using 2 layers of Tensar NX850 stabilizing geogrids, we were able to make a significant saving in the construction costs. And this is also something that the software automatically provides you. It's a cost estimate of this working platform, including the savings, but not only in monetary value, also in time. Imagine that if a contractor is able to build twice as many projects with the same amount of people and machinery, that he will be able to do more projects in a year. And of course, not the least important, maybe the most important aspect, we are able to save in environmental impact of this working platform by saving the carbon footprint. Of course, when we need less quarried stone or less transportation, we require less dump truck visits, less fuel, and less compact water for compaction, we will save on environmental impact. And these values are significant. Thanks to our D-value design approach and Tensar Plus design software in 2004, last year, we were awarded Tensar and the University of Birmingham received the award for their real scale temporary working platform using the Tensar D-value method, where we were able to achieve 75% reduction in carbon costs. And this award has been awarded to us by the Federation of Piling Specialists themselves. Okay, so last thing before we go to the question and answers is our live demonstration of Tensar Plus design software. When you go to tensarplus.com, you'll be asked to make an account, to sign up. And once you're logged in, this is the screen that you see. You have the option to set some parameters, like the country where you're from, which will then automatically populate the available design methodologies and the documentation for you, but also the currency. As you can see here, I am based in the Netherlands. So it is set to the Netherlands, and we have this option to go to platforms. And we have working platforms, but I will show you here the tracked plan section, because here, this is where I made the example that was from the presentation. You can see here I can put in the load cases in a triangular, trapezoid, or rectangular shape. You can have two different load cases. You can freely use based on maybe two different cranes or two different hoisting schemes. You can put in the lengths, the width of the track, the pressure coming from the track. We can define a required factor of safety. This can be anywhere between 1.6 and 2 or even higher. We need to say something about the material that we used. We have the option to put in a high quality crushed rock or a medium quality recycled aggregate. We can define the largest particle size. We can choose the type of geogrids. We can define a cohesive or a granular subsoil, either with the undrained shear strength or a friction angle. We can add in the influence of groundwater, and the software automatically calculates the required thickness, both stabilized with Tensar geogrids and unstabilized. And if we go to the Value tab, we can see the savings that have been achieved based on total area of the working platform. See here that we have some standard populated numbers for the material costs. Of course, you are very free to change those to represent your local values. And even if the geogrid is expensive, the total costs of the working platforms are significantly lower. We have the option then to print out this design, so we can add it as part of a design documentation. You have the ability to opportunity to put in the project information in. Savings are of course specified, and all the other design parameters and considerations are transparently available for evaluation and comparison and checking compared to the published papers. We can also print out a specification for as part of a tender, so the contractor knows what to order. So here we have the specified granular material that is being assumed to be used for this project, and the properties of the geogrid. Of course, all the input design parameters. You can freely and easily share this design with any colleagues, or if you need assistance from Tensar, using the share button. Because this example is not saved, I will not be able to share it, but if I open up the webinar example, which you saw earlier, now I can share it, and I get this nice link that can be sent to anybody for reviewing. And anybody that has a Tensor Plus account can open up the design and review it. The last thing I want to show you is our resources. Of course, I've given you the presentation now, but in the software itself, we can go to software information and we can go to new extra information about design methodology, testing, the validation. Everything is freely available. How does the t-value method work? Again, a summary of how we derive the parameters. Everything is available for you. We have installation guidelines, we have case studies, and we have extra information on our geogrids. So everything is available to you